Back in 2014, one deceptively simple idea just completely changed the game for how we teach computers to see. It was a massive breakthrough for AI, and today, we're going to break down the story behind the landmark paper that made it all happen, VGGNet.
So, here's the fundamental question, right? How do you get a machine to look at a picture and not just see a bunch of pixels, but to actually understand what's in it, to know a cat from a car? For a long time, the solutions people were coming up with were getting more and more complicated. But then, this team from the University of Oxford came along with a totally different take. It was elegant, it was powerful, and, as you might guess from the title of their paper, it was very, very deep. Okay, so to really appreciate just how big a deal this was, we first have to understand the world they were living in. There was basically this high-stakes race going on to build the best artificial eyes on the planet. And the premier event for this was the ImageNet Challenge. Seriously, you can think of it as the Olympics of computer vision. Teams get millions of images, and their AI has to figure out what's in each one, choosing from 1,000 different categories. It's an incredibly tough problem, and it was the ultimate proving ground for new ideas. And before our story really kicks off, the trend was all about making these small, really intricate changes. Researchers would endlessly tinker with things like the size of the filters that scan the image, or how many pixels the filter jumps at a time. Progress was happening, sure, but it felt complex and kind of incremental.
And this is where the team from Oxford's Visual Geometry group, yep, that's where VGG comes from, took a step back. Instead of adding more complicated bells and whistles, they just asked a really simple question. What if we stop trying to make the network fancier and just make it deeper?
This slide lays out that shift in thinking perfectly. On the left, you've got the old way, using these big, clunky filters, like an 11 by 11 pixel window, to spot patterns. But VGG's idea, on the right, was totally different. They said, let's use stacks of tiny, simple 3 by 3 filters, but just a lot more of them, in a much deeper chain.
So why on earth is that better? Well, this is where the genius comes in. It turns out that a stack of 3 of those tiny filters can see the exact same area as one big 7 by 7 filter. But, and this is the key, instead of making just one calculation, it makes 3 separate ones. After each little step, it gets to make a decision about what information is important. The more decision points you have, the better the network gets at learning complex patterns. And the kicker? It's actually way more efficient, using 81% fewer parameters. It's smarter and lighter.
So, the VGG team had their hypothesis. Depth is the secret sauce, and small stacked filters are the way to get it. But, an idea is just an idea. Now they had to prove it, and they did it with a really methodical, scientific approach.
They didn't just build one network and call it a day. No, they built a whole family of them, which you can see right here. They started with what they called Network A at 11 layers deep. Then they just kept adding more of their 3 by 3 filter layers, going deeper and deeper, all the way up to Network E, which had an incredible 19 layers. By doing this, they could perfectly isolate the effect of just one thing: depth.
And they were super clear about their goal. In their own words, right from the paper, they said their main contribution wasn't some flashy new algorithm, but a thorough evaluation that proved you could get a significant improvement just by pushing the depth of the network. No magic, just depth.
And that, of course, brings us to the results. All this work, this beautifully simple hypothesis, these careful experiments, was it all worth it? Did it actually pay off? So, the million-dollar question, did going deeper actually make the network better at seeing? Well, the answer they got from their experiments was a massive, undeniable yes. And this chart just shows it so clearly. Now, on this chart, a lower bar is better. That's the error rate. And just look at the trend. As they go from the 11-layer network to the 13-layer one, the error drops. By the time they get all the way up to their 19-layer model, the error has fallen by a huge amount. The data was screaming, deeper is better.
And the final number was just stunning. When they put their best models together, they achieved a final test error of just 6.8%. This absolutely blew past the winners from the previous years and locked them in as one of the top performers at the 2014 challenge. Their simple idea had worked spectacularly.
But here's the thing. Winning a competition trophy? That wasn't the real prize. The true impact of VGGNet was that it laid a whole new foundation for the entire field of AI and computer vision.
So the VGGNet paper did a few absolutely critical things. First, it proved, with data,
that depth was a key ingredient for performance. Second, it gave the world this simple, elegant blueprint for building powerful networks. And because it was so simple, it became the go-to backbone for all sorts of other tasks. But maybe most importantly, the authors released their trained models to the public for free. This let anyone build on their work, and it just kick-started this massive wave of innovation across the field.
And if you're wondering, why does this matter to me? Well, the core ideas from this paper are now everywhere. That principle, that depth matters, and that simple, repeating blocks can build incredibly powerful systems. It's at work inside your phone right now when you search your photos for dog, and it's helping doctors analyze medical scans to find diseases earlier than ever before.
It's amazing to think that this whole revolution started with one simple, powerful question. It really makes you wonder, if just simplifying an idea and pushing it to its absolute limit could have this kind of impact, what's the next simple, elegant idea that's out there just waiting to be discovered?